Well, thank you very much, considering how late we are. And I'm the last speaker before dinner. I'll try to hurry up a bit. This is work mostly done by my PhD student, Andreas Bechtold, in collaboration with a number of people, mostly from Vienna. Now, we're dealing here with a lunar meteorite, one of several hundred by now, which interestingly enough, the total weight of lunar meteorites by now far exceeds the mass of samples brought back by the Apollo missions, which is hasn't been the case for a while. Anyway, we're looking at a fine-grained polymeric lunar breccia. First results on classification and composition were reported by Bechtold and others in Meteoritics and Planetary Science in 2021. It has a mass of about 85 grams, which was acquired by the Natural History Museum in Vienna in 2004 from a Moroccan meteorite dealer. Interestingly, the composition in terms of lithic and mineral classes in bulk chemistry shows quite an interesting mixture with influence or indication of Mare region components, particularly, for example, in terms of high energy, high titanium abundances in minerals and glasses. The major and trace element compositions of this lunar meteorite determined from a homogenized bulk powder were measured by neutron activation analysis and then a few other methods. A lot of thin sections were also studied. In total, the ion concentration is putting this into the intermediate ion concentration group. Thorium concentration is consistent with the Procellarum creep terrain as a possible source region. We're going to expand on that in just a moment here. There are lunar meteorites in general that have intermediate ion concentrations, and for example, a plot of aluminum versus iron is used. Here we're looking at the fields of feldspathic lunar meteorites and basaltic lunar meteorites, and some components are plotting somewhere in between here. And of course, Mare basalts have differences in chemical composition from those of the highlands. So titanium concentrations in Mare basalts have been measured in a variety of ways. For example, there are Mare basalts that show distinct concentrations as indicated in this particular image from Lunar Prospect. The wide angle camera shows the titanium concentrations approximated, of course. We did a number of analysis of minerals and glasses of this particular lunar meteorite from a variety of thin sections. And the glasses and clasts are plotted here with various stars and triangles and X's and so on and so forth, together with titanium-rich and medium Mare basalts. Data sources are in our original paper in 2021 in MAPS. Similar also for the iron versus titanium plot. Looking at strontium or rubidium strontium isotopes compared to a variety of lunar samples, it is noted that Northwest Africa 11962 plots somewhere near the Apollo 15 soils, but towards the creep range. Similar observations can be made for some neodymium isotopes, again plotted versus selected lunar samples. So there's some Mare trend, but towards the creep terrain. We also looked at highly siderophile elements, for example, iridium and osmium, also a few others. Older data from Paul Warren and others indicate, for example, for Regolith Breccia lunar meteorites, Elm Hills 8105 and Yamato 791197, noted iridium and osmium contents on the range of about 7 to 8 nanograms per gram. What we see here is particularly lower, excuse the typo in magnitude. Pristine lunar rocks have a lot lower highly siderophile element concentration, so there is a meteoritic component that seems to be present here. So we studied this in a little more detail using some more isotope systems and abundances. Here's a diagram of osmium over iridium versus the osmium isotopic composition. And if we look at these, then we see that we have a trend line for iron meteorites, the 4A iron meteorites, close to which, or at least on the lower end of which, this particular lunar meteorite 11962 plots. It is also not too far from some ordinary chondrites, but farther away from some of the other meteorites. Of course, since we have a mixture of clasts and components here, we're looking probably at a mixture here. So in addition, in a paper published late last year, also in Meteoritics and Planetary Science, we tried to constrain a source crater and compared the abundances of mostly the elements iron, thorium, and titanium, measured by a variety of remote sensing methods from Lunar Prospector with the lunar meteorite composition, and comparing that area with a list of relatively young 0 to 1 million year old impact craters, young small impact craters. Now, some of the young impact craters, they are the white dots shown here with diameter of about 300 meters or larger. There is one of them that is within the potential source region, as indicated by the chemical composition of Northwest Africa 11962. And this source region and the crater are located at the southwestern limb of the Procellarum creep terrain. And therefore, impact breccias are also known to have some extralunar component with iron meteoritic contribution. So we conclude that we have a lunar regolith breccia with a bulk chemical composition that is comparable with an origin from the Procellarum creep terrain. There is a meteoritic component that could be dominated by iron meteorite, maybe 4A, but also maybe a little bit of a chondritic component. And there's a potential source crater that could be identified. There are ways how to identify source craters. Here we have a particular way how it was done. Details are in the publication in Maps, from where a Python script can also download it as supplementary material. And with that, I think I have caught up at least 2 minutes or something like that. Thank you for your attention. All right.